Good evening, everyone. Welcome to the Midtown Scholar Bookstore's virtual event series. My name is Alex. I'm with the Scholar, and as always, I am live in Harrisburg, Pennsylvania at the bookstore. Thank you for tuning in this evening as we welcome Katie Mack and Sean Carroll to virtual Harrisburg. We have a really awesome program for you tonight. We're happy you're here, so thank you for tuning in. Thank you for supporting the bookstore, and we hope you enjoy the event. But at this time, I'd like to tell you a little bit more about our speakers here this evening. Our interviewer is the one and only Sean Carroll. Sean is a theoretical physicist at the California Institute of Technology, host of the Mindscape podcast, and author of From Eternity to Here, The Particle at the End of the Universe, The Big Picture, and Something Deeply Hidden. He has been awarded prizes and fellowships by the National Science Foundation, NASA, the American Institute of Physics, and the Royal Society of London, among many others. Of course, our featured author this evening is Dr. Katie Mack. Katie is a theoretical astrophysicist exploring a range of questions in cosmology, the study of the universe from beginning to end. She is currently an assistant professor of physics at North Carolina State University, where she is also a member of the Leadership in Public Science Cluster. She has been published in a number of popular publications such as Scientific American, Slate, Sky and Telescope, Time, and Cosmos magazine, where she is a columnist. Of course, the book we are here for this evening, now just released in paperback, it's titled The End of Everything, Astrophysically Speaking. I've got to read this just one blurb from Science magazine, which I like. They said, excellent. The book is the perfect antidote to the malaise of mundane worries, end quote. A couple of housekeeping notes before we get started. First, if you have a question at any point for Katie or Sean, please use the Q&A button towards the bottom of the screen. It's below our faces here. We love questions from the audience. We want to hear from you. So ask away, and we'll try to get to as many questions as possible towards the end of the program. And lastly, maybe most importantly, if you enjoy the talk and want to support the bookstore, please consider purchasing a copy of the book from the Midtown Scholar. While this event is free to you out there, it is not free to us, and every purchase helps support this event series, our staff, and the future of the bookstore. We are even offering a limited time book bundle, here both books, for a discounted price of $30. So if you want both The End of Everything and Something Deeply Hidden, you can get a copy of that through the bookstore. I'm going to drop a purchase link in the chat room in just a moment. Click on that. It will take you to our website, midtownscholar.com, where you can grab a copy of the book. And once again, thank you everyone for tuning in and for your continued support. But now I'm happy to hand it off to Katie and Sean.
Thanks very much, Alex. Thanks everyone for being in the audience. It's always great to be back in Pennsylvania, even if virtually. I'm from Pennsylvania myself, so I miss going back, but this is a good excuse to sort of experience it, even if a little bit indirectly. And it's great to be here talking to Katie, who is a wonderful author, and her book is great. You should all buy it if you haven't already. So Katie, let's start with the obvious question. I mean, you've written a book about the end of the universe. So, yes. I mean, is this your fault? Did you do something wrong? Something go terribly wrong in a research problem, and you've brought about the end of the universe?
So it is definitely not my fault. I've been interested in the question of the end of the universe for a long time, and I realized at some point that I keep getting sort of sidetracked from my usual research problems to think about different dramatic ways the universe might end. So, first I started reading about the Big Rip, this idea that the universe could be torn apart by dark energy, and I would tell everybody I knew about that possibility, and then I worked with Paul Steinhardt at Princeton, and he has an idea about the beginning and end of the universe, where there's a cyclic universe where sort of everything ends in this fiery new Big Bang, and I thought that was really fascinating. And then I started learning about vacuum decay, sort of very sudden ending of the universe, and that was fascinating. I realized that there have been a lot of books about the beginning of the universe, but really very few about the end. And I thought it would be just a lot of fun to go through some of those exciting possibilities and talk about kind of where we're at with this question, how we're trying to figure it out, and what it would look like in these various scenarios, what we would observe, how it would happen, what the physics is that tells us about these different options.
And for the practical minded among us, I mean, is this a survival manual? Is this like, I mean, why are we doing this? Why are we asking this question? Is this going to give us a way out or a way to make it happen?
Sadly, no. I mean, it's we definitely are not going to get away to make it happen, which is good. Although that is something I have done a little bit of research on, like, can any of these things be induced? And as far as I know, that does not look possible, which is great for us as
Would you tell us?
existing. I wouldn't tell you how if I figured it
Okay.
out. There are some sort of ethical constraints on that sort of research, I think. But no, it's I think the reason to ask these questions is just to better understand kind of where we are in the cosmos and how everything fits together. And it's so this book is not in any case in any way a manual or practical. There's no sort of practical application to thinking about the end of the universe, but I do think it touches on something really fundamental about who we are, which is that we have curiosity about our place in the universe. We have curiosity about where we came from and where we're going and what that whole story is. How does everything fit together? Is there something that will sort of wrap everything up and make it all make sense at the end? I think I come down on the side of not really. There's we might find out how it's going to happen, but if you want really to know the meaning of it all, that's a kind of different question. And in the book I do talk about that a little bit, and I talked to a bunch of different people about how they conceive of that notion of what does it mean to live in a universe that will end, and we do think it will end. That is one of the things that all of these different scenarios have in common, that there is an ending. There is something that, at least from the perspective of is there anything remaining in the cosmos that is meaningfully existing? In all of these scenarios, the answer is no. So
we don't have like a fun kind of interesting lifestyle like we have now that could last forever, is what you're saying.
Right. Yeah, exactly. Like the universe is evolving toward something that is less survivable than it currently is in. And when I say the universe for that purpose, I'm talking about the observable universe, the part of the universe that we live in. There could be other regions of space that are beyond our observation, that have different histories, different futures, that might carry on after we're gone. But the universe as we see it, as we experience it, as we observe it, is changing. It is evolving, and that evolution is not toward more life and more order and more structure. It's toward disorder, entropy, the destruction of all things.
All right, so good. We're just coming out of a global pandemic, and you're here to tell us that the whole universe is going to end before we get too happy about our current situation. I'm sure that the audience is really thankful for that.
Well, it's almost certainly going to be a very long time from now. So
okay, that's the good news. That is good news. Yeah.
All
right. So, I mean, maybe I want to hear about all these different scenarios for how the universe might end, because we don't actually know the one true answer. But maybe the way to get there is to first say a little bit about what the universe is doing now, right? I mean, we know more about the present and the past than we do about the future.
Yeah. So we really do know a lot about the history of the cosmos. We know a lot about the beginning of the universe. So there's the place where it gets uncertain in terms of the beginning of the universe is really very early. So we have extremely direct observational evidence about the universe from about 380,000 years of age onward. And given that it's 13.8 billion years old, that's a pretty good stretch, right?
Yeah.
We're talking about some uncertainties that are within that 380,000 years. And even beyond that, we have extremely good sort of theoretical models and experimental evidence of how physics was different, down to sort of millisecond timescales, where we can recreate the conditions that the universe was in at those very, very early times. The reason that we know all these things is that we see that the universe is currently expanding, and what that looks like is that distant galaxies are getting farther apart. Everything in the universe seems to be getting farther apart. The universe seems to be getting more sort of diffuse, emptier in some sense. And so if we just kind of dial that back in time, we see that everything was closer together. The universe was more dense. The universe was hotter. And so the natural conclusion is that there was a time when the universe was very hot and very dense, and space was not empty, but filled with sort of plasma, this energy. And that we actually do see that. We actually do see that stage of the cosmos, because when you look into the distance, you're looking into the past, and so we can look into the distance so far that we can see the universe as it was in the very early stages when it was still on fire. So that's the direct observational evidence of the Big Bang. We really do see that, which is astonishing to me still, just thinking about the fact that we can look at the universe as it's on fire. Parts of the universe are so far away that from our perspective, they're still in the Big Bang. And then, we also can extrapolate that the universe was even hotter, even denser earlier on, and we can do experiments that can recreate those conditions. So our story of the universe, starting from around a millisecond, or depending on how much faith you put in some of the theoretical and experimental evidence, you move that around a little bit. But that story is extremely solid. And there's some uncertainty about the very, very beginning, especially about sort of billionth of a billionth of a billionth of a second after whatever started the universe, and what started the universe. There's some mystery around that. But then the rest of the history of the cosmos, we have a very good handle on in a couple of different ways. And so we can use that to extrapolate about the future.
So it's about 14 billion years since the Big Bang. The universe has been expanding. I'm going to ask you some questions that I always get asked myself. So I just want the audience to know that some of these I know the answer to, but I'm going to let Katie answer them.
Yes.
So if the universe is expanding, how big is it?
Well, so what we can measure is the observable universe. And again, that's the region of the cosmos that we can measure. We can see, so we are pretty sure the universe goes on much farther than that. In fact, it may be infinite in size. We don't know. What we do know is that there's no evidence for an edge. There's no evidence for any boundary in space to the cosmos. There's a hard limit to how far we can see based on the speed of light. And what that limit derives from is just the fact that if a beam of light started sufficiently far enough away, it would take longer than the universe has been around for it to get to us, because it has to travel through space, has to move at the speed of light. And so we can only see light that's been traveling toward us for less than 13.8 billion years. And that gives us a horizon. That gives us a distance out to which we can't see beyond. And that defines the observable universe. But when we get that information, we don't see any evidence that something's suddenly changing at that point. And and we have other reasons to believe, based on our theories about the very beginning of the universe, that it probably goes on much, much, much farther than that in a very similar kind of way. But that distance toward where light has traveled for 13.8 billion years, that distance is actually about 46 billion light years. So a light year is the distance light travels in a year. You would think that it would be at 13.8 billion light years, the edge of our observable universe. It's actually farther than that, because the universe has been expanding since the beginning. So a point that sent its light to us 13.8 billion years ago is now 46 billion light years away.
Okay, so it's very big, getting bigger.
Yes.
And it's getting bigger faster, they tell me. Like there's something that is pushing the universe apart. What's that all about?
Yeah, that's like the weirdest thing in the universe, and the most important thing in the universe is dark energy. So in the late 1990s, astronomers were trying to figure out what the universe's expansion was doing. And the idea was that there are kind of only three possibilities, right? One is that the expansion is going slowly enough that the gravity of everything in the universe is slowing it down enough that it would stop at some point. The expansion would stop, everything would kind of fall back together. So this is an analogy. The analogy is like if you throw a ball up into the air, if you don't throw it fast enough, then the gravity of the earth pulling on the ball and the ball pulling on the earth as well, pulls them back together. And, so it slows it down. At some point it stops it, and then the ball falls back down to the earth. If you were able to throw the ball at 11.2 kilometers a second, you could throw it at more than the escape velocity of, you could reach the escape velocity of the earth. It would continue slowing down, but it would never stop, it wouldn't stop and fall back. It would just keep going into the cosmos, always slowing down. And if you threw it faster than that, you could get to the point where it would kind of be coasting at a sort of constant speed out in the cosmos, forever. But those seemed like kind of the only possibilities. And in the 1990s, astronomers discovered that actually what's happening in the cosmos is that the expansion is not slowing down at all. You would think that gravity has to be slowing it down, but what it was doing was speeding up. And that's about as weird as if you throw a ball up into the air, it slows down for a little while and then shoots off into space. And we didn't have a good explanation for why the cosmos was suddenly expanding so quickly. So we called whatever's making that expansion accelerate dark energy. It's also, it's likely or possibly something called the cosmological constant, which is just a sort of property of space that has this expansion built into it, into the equations of how space evolves. But whatever it is, we call it dark energy. I know that you've proposed a better name for it, which is smooth tension. So this it's whatever it is. It's very smooth. It's just kind of stretches out the cosmos. Calling it dark energy is a little bit iffy. Not dark. It's invisible, and energy is a little bit of a vague term, but whatever you call it, it's something that's making the universe expand faster, and that's all it does, as far as we know.
Do we think that this dark energy is not only making the universe expand, but if galaxies are moving away faster and faster? Is that something like there's a certain fuel source that we're run out of and it'll all just peter out and recollapse, or can the dark energy keep pushing it apart forever?
So we don't know if it'll keep going forever. If it is a cosmological constant, which means just a property of space itself, then yes, it will continue forever. When there's more space, there's more dark energy. It just keeps, it keeps pushing everything out. It could be something that is dynamical. It could, by which we mean it could change over time. It could be some kind of field that has some behavior where it's currently causing expansion, but maybe it'll turn around and cause recollapse. We don't know what dark energy is. We don't know how it's going to behave in the future. So we're studying how it's acted in the past. We're studying the expansion history of the universe, the history of the buildup of structure in the universe, and trying to use that information to deduce, is it really a cosmological constant, something that is just a property of space that'll continue forever in the same way, or does it have some more sort of interesting, cataclysmic behavior?
So you're telling me that before we discovered the cosmological constant, we had these options that the universe could either expand forever or it could recollapse. And now that we discovered the cosmological constant or dark energy or the acceleration of the universe, we still have those same options. We're still not sure whether the universe will recollapse or not.
Yeah, we're just more confused about both of them. Right?
Okay. So, but we have a hint that we have ways of actually testing to at least get some hints.
Right. So if it's a cosmological constant, then we have a very good understanding of the history of its effect on the cosmos, the history of its effect on structure in the cosmos, and so we can test that. We can see if there's any deviation from that effect. So it should be something where the density of it is constant even as the universe expands, because it's tied to how much space there is. It's not independent of space, and so when there's more space, there's more dark energy, and the density just stays the same. The amount of energy density per unit volume stays the same. And so given that, then we can trace, how it should have affected the expansion of the universe in the past, how it should have affected, how galaxies and clusters of galaxies came together in the past. And then we can see if the behavior of dark energy is consistent with that. If we find it's not consistent with that, then that's a clue that something else is happening, that it's a more interesting kind of dark energy, a dynamical dark energy, sometimes called quintessence, something that is changing with time. And then there are possibilities where maybe it doesn't change with time, but it also has a slightly different, or it doesn't change its behavior with time, but its density is either going up or down with time, because it's not tied just to the amount of space there is. And then you get interesting possibilities there too. And so we're starting to be able to test that. And there are theories about kinds of weird dark energy that have laboratory consequences as well. So there are certain kinds of dark energy that are connected with some kind of scalar field, which is a kind of energy field that exists through all of space. The Higgs field is an example of this, which we'll probably talk about later. So if it's some kind of scalar field, it might have interactions with other fields and particles that we could test in the laboratory. So it wouldn't just be stretching space, it could be doing something else too that we might be able to find in laboratory tests. So that would be helpful and exciting. And if it's a cosmological constant, unfortunately, we can't ever prove 100% that that's what it is. We can just say it doesn't deviate from that behavior to the precision of our measurements.
So if it is a cosmological constant, then this amount of density of energy that is pushing the universe apart is just strictly constant. And there's only one way to be constant. There's a billion different ways to be not constant, right?
Exactly.
So we can't ever say that it is a cosmological constant. We could say that it's not, right?
Right.
So the data, I presume that the data right now are still completely compatible with the dark energy just being a cosmological constant.
Yeah. I mean, there's, we have some uncertainties in our measurements based on limitations to what we can observe. And so far within that uncertainty, it's totally consistent with a cosmological constant. So that's sort of the default idea that it is a cosmological constant. And that gives us a particular ending of the cosmos that's the sort of expected version of what happens.
So, but before we get to those details, I just want to, let's be nice to the audience and share your credence that it really is the cosmological constant. I mean, what are the odds that you put that it's just a cosmological constant versus something fancier and moving and dynamical and stuff like that?
I mean, I think I guess for me, I take that as the null hypothesis. I take it as the default idea. I think that's something that makes sense to me because it seems very simple, and it fits all the data. There are some subtleties to it, which is that the best way we've tried to explain really what a cosmological constant is to say that it's somehow connected with the vacuum energy, the energy of space itself, per se. And when we've tried to calculate that from first principles, from what we know about how particles interact with each other, what we know about quantum mechanics, we get a totally different number in a really shockingly different way. So if it is a cosmological constant, we really don't understand where it comes from, like why it is the value it is, why we have the amount of expansion we do. So that's a big mystery if it is a cosmological constant. But the idea that it is just sort of a property of the universe, I guess I take that as the default idea. I guess, if I had to put money on something, I would put money on that.
Okay.
I don't know. Is that what's your take on it?
Yeah, no, I certainly think the same thing, but I would just say it even more definitively. I think that it's at least a 90%, more like 95, 97% chance of being a cosmological constant. So we have to keep an open mind, because if it's not, you win another Nobel Prize for finding out whatever it is, right? So it's a big deal.
Well, but whoever discovers it, yeah.
I didn't mean you personally, but it might be you. You're in the running. You can do it. But so if that's the most likely thing, given what we currently know, let's be very clear about what the future of the universe holds if it really is a cosmological constant.
Yeah, so the story, if it's a cosmological constant, is fairly simple. What happens is the universe continues expanding forever. It continues accelerating in its expansion forever. And the consequence of that is something we're already starting to see happen, which is that distant galaxies are moving so far away from us so quickly that we will stop being able to see them. So there are already galaxies that are moving away from us so quickly that they're moving away from us faster than the speed of light. Now, what I mean by that is not that they're moving through space faster than the speed of light. You can't do that. But that there is so much space appearing between us and them that from our perspective, they appear to be moving away faster than the speed of light. There is more space between them such that light cannot catch up as it moves through space at its own speed limit, which is the speed of light. And so there are already, galaxies are kind of disappearing from view. There are galaxies we can only see as they were in the distant past because the light started coming toward us when they were closer to us and when they were not moving away so quickly. And now we know that they are moving away so quickly that we would not be able to see any light that they sent to us now. And if we fast forward this picture about 100 billion years, we'll get to the point where none of the galaxies are visible to us, where all of them are moving away. All of the ones outside of our little local group of galaxies are moving away from us so quickly that we can't see their light anymore. And at that point, you're really in a universe that's just decaying. So once the other galaxies are moving away so quickly, then all we have are the stars within our own galaxy. And I mean, by that time, our galaxy will have merged with the Andromeda galaxy and the Triangulum galaxy and the little group of galaxies we have here in our little group of local galaxies. But in our sort of, monster galaxy, there will be stars. They will not be actively forming anymore because one of the things that triggers star formation is when galaxies collide with each other, bring more gas together, that triggers new bursts of stars. And that's happening less and less often as galaxies are on average getting farther and farther apart. And you can actually, one of the funnest things I encountered when learning about this topic is that, you can actually calculate how many stars formed in the distant past, how many stars are forming now, and that's sort of the rate of star formation in the cosmos. And you find that there was a peak of star formation that happened sort of, I think 6 or 7 billion years ago. And then, no, it's more than that, like 9 billion years ago. And then since that time, the amount of star formation has just been dropping as galaxies are on average getting farther and farther apart, and the gas within galaxies is getting used up. And so you can kind of follow that graph and see, predict for the future how many stars are going to be forming in the future. And what you find is that at this point, 90 or 95% of all the stars that have ever been or ever will be have already formed. And so from now until the end of time, if we go on this timeline, then all that's left is the last 5 or 10% of stars. And so we're almost done.
Do we know when the last star will burn out? Because individual stars don't last forever either.
Right. Well, different stars have different lifetimes, and the more mass of the star, the shorter the lifetime. So we know that there are currently stars in the universe that are low mass, such that no star of that mass has died yet, because their lifetimes are many billions of years, even trillion years. So there are some that have time scales of a trillion years or so. The smallest ones. But then once they stop forming, those are just going to die. And so once we get to this point where other galaxies are invisible, if we have our Hubble Space Telescope version, 20.0 up there orbiting whatever's left, it's going to be seeing a few dying stars in our mega galaxy, and it won't see any other galaxies in the universe. You won't get those beautiful pictures of spiral galaxies. It'll be a couple of dying red stars and black, and then those stars will die. There'll be some black holes that, according to current theories, will be sort of evaporating. So there'll be little bright dots of light where these black holes are emitting some radiation as they are dying. And then over time, those will burn out and the stars will be gone, and then particles will start to decay. We think probably protons will eventually decay, and then the universe will be left essentially empty, and all that will be left will be this sort of trace amount of radiation that's kind of floating through the cosmos, and it's essentially the waste heat of all of reality. It's everything will decay into entropy, into disorder, and that waste heat will be all that's left, and that's called the heat death of the cosmos. Right. And that appears to be where we're headed.
So the heat death of the universe. So all the galaxies move away from us. We merge with our nearby friends. We make a few more stars, not that many. Those stars burn out. The particles and the black holes all decay, and we're left with nothing but empty space. And you're saying that's the default. That's what you think is the most likely thing to happen. And it's empty, dismal eternity forever.
Yeah. Yeah. Okay. Unfortunately, good. It's a sad story.
Yeah. Does it seem like a little weird? Like, we're contemplating these big questions, and of course we can always be wrong, especially when we go to the future, right? But is there some imbalance that worries you about the fact that you're saying the universe is 14 billion years old since the Big Bang, which sounds like a lot, but then it's infinity years old toward the future? Is that like a weird universe? Like, it lasts for, there's an infinite amount of universe and we're right at the beginning.
Yeah, and we don't know. We don't know if something else will happen once we get to a heat death universe. So there are some proposals, and you and I have talked about these, where you could have a new universe kind of pops up randomly out of the this extremely cold heat bath of the post heat death cosmos, and whether or not that's likely to happen depends on how you calculate it, and there are differing opinions on if that can happen. But there are some ideas where something can pop out of this sort of spent cosmos. But then there's also ideas where the heat death evolves into a new Big Bang through a cyclic universe. So Roger Penrose has been discussing this idea where you can have a sort of a Big Bang sort of stuck onto an end of the heat death scenario, where the whole universe kind of is reborn, and a new universe comes out of that. There are some ideas where something comes out of the end, but if you just take the default equations and just kind of carry them forward, you don't run into something, right. If you just take what we know about, it just keeps going, and the temperature reaches kind of a constant level based on complicated things to do with quantum mechanics and horizons. But anyway, you just end up with this sort of steady state of a constantly expanding, accelerating universe that has nothing of interest in it.
So it clearly depends on what we're eventually going to figure out about the dark energy. Like, that was, we went through the heat death. If it's constant in density, it comes to dominate the universe. I guess there are two other possibilities. It could go up or it could go down. Yes. So what if the dark energy density actually goes up with time? Is that a plausible scenario?
Whether it's plausible also depends on who you ask. There's disagreement about that among physicists too. Right, yeah. So most would say that it's not plausible, but we don't know. And so there are scenarios where the dark energy density does go up in time, and that's called phantom dark energy. Nice scary name. And what happens with phantom dark energy is the heat death, although it's a sad story, is a fairly gentle way to go. Everything just kind of fades and gets colder and darker, and just kind of peters out. If the dark energy is going up over time, if the density of the dark energy is going up over time, then not only does it move galaxies away from each other, it starts to expand them from within. So right now, the universe is expanding. This room is not expanding. Our galaxy is not expanding. Anything that's already sort of gravitationally bound together is not getting puffed out by the dark energy. Because basically, if you're trying to form a galaxy, you're putting a bunch of matter together. If that can beat the dark energy, the cosmological constant when it forms, then that volume of space is never going to have more cosmological constant in it because it's a constant density. So it's never going to change that balance. So the gravity already won. So it's stuck forever. But if you have the dark energy density going up with time, then you've made this nice stable galaxy, and suddenly there's more dark energy kind of pushing everything apart. And so it starts to kind of pull the galaxies apart, starts with the clusters of galaxies. It kind of pulls galaxies out of their clusters of galaxies. Then it starts to pull stars away from their galaxies. And then the scale goes down. So it starts to pull planets away from their stars, and then starts to actually build up within solid objects like planets and stars. And stars are not exactly solid, but anyway, it starts to build up within objects. And you can calculate that eventually, and you can calculate exactly when it'll happen. If you know exactly what this stuff is made of, you'll find that it will tear apart the smallest things, atoms, molecules, nuclei, and the entire universe. And that's called the Big Rip. And the reason that you and most physicists would say it's not plausible is because if you follow that through, you run into some problems with energy conditions, which are, sort of principles we think govern how the structure of space works. But we don't know for sure if those things hold on these scales and in these contexts, and we don't know for sure that the dark energy is going to stay constant as a cosmological constant. So it's definitely a fun thing to think about. I mean, not, you wouldn't want to be there. It's a terrifying thing to think about, but it's fun to think about the physics of the idea that at some point the universe could be ripped apart in this accelerating kind of way where you would see it coming, right? Like you would see the clusters of galaxies being unraveled. You see the galaxy starting to lose its stars. You would see that it's coming for you, and that would be really dramatic.
Yeah, and so I guess the Big Rip is sort of, we agree that there's issues with it from a physicist's point of view, but it's very vivid and it's on the table as a possibility, so we should think about it.
Yeah, observationally we can't rule it out, and in some ways the observations are sort of a little bit on that side, although the error bars are very much holding the cosmological constant within those, so we can't actually distinguish.
So is it sort of easier or more physically plausible to imagine the dark energy just fades away and either the universe still empties out or maybe even starts to collapse?
So it violates fewer energy issues if you have it turning around. So that if you have it that the dark energy is not just building to this crescendo of tearing everything apart. So you could have a field that governs the expansion rate that turns around and pulls things back together, and that's if we had a field that were acting in that way, if we had something that was able to affect the expansion of the universe in that way, we couldn't say that it's totally impossible from a physical point of view. And there are ideas about dark energy where it evolves over time in such a way that it could sort of turn around. None of those are favored models, so they're very speculative. But you could have a situation where the universe could come back, recollapse if the dark energy drastically changes its behavior, and that would be very dramatic. That would be a big crunch. Which would be, I think, terrifying in a different way. So because you would also see that coming, right? And to me, that's the thing that makes some of these ideas terrifying. That is that you would, we live in a huge universe that doesn't care about us at all, and we were at its mercy. And so the idea that what you would see in that case is you would see that the galaxies are now coming toward us instead of moving away, and you would see that space is getting hotter. So if the big crunch is coming, then what's happening is that space is compressing, and it's compressing all of those galaxies into smaller spaces, but it's also compressing all the radiation, just the ambient radiation of space into a smaller region. And at the same time, making that radiation harder radiation. So right now, the universe is full of this microwave background radiation, which is the kind of afterglow of the Big Bang, this light that we can see at the distance of the trace of the plasma of the early days of the universe. So there's this microwave radiation at very low level that's all throughout the universe. But if the cosmos is compressing, then it's compressing all that radiation into smaller regions. It's also making, dialing up the intensity and the frequency of that radiation.
Right.
So it's turning it into, radio visible light or infrared visible light, and hardening that radiation. And it gets worse because there's also the radiation from all the stars that have ever shown in the universe, and that's visible and ultraviolet. And then there's the radiation from high energy cosmic events, and that's X-rays and gamma rays, and all that radiation gets compressed as well. So in a big crunch, the scary thing is not a galaxy colliding with another galaxy, because that happens all the time, and it can get messy, but it doesn't. The stars themselves don't collide with each other. There's just a lot of empty space even inside a galaxy. But the scary thing about a big crunch is that space just gets really hot and really dense, and it can get so intensely hot that it starts to cook stars from the outside. So you get eventually this situation where the stars start to have thermonuclear explosions happening along their surfaces from the ambient heat of space, just the radiation throughout space. And at that point, there's no surviving anything. Once the stars are getting cooked, that's it. So that's to me the scariest possibility, and also a very unlikely one, of course, because we don't know of a mechanism for that to happen at the moment. But the idea that you would just be sort of slowly cooked by space itself, by the ambient radiation of space, is a little bit terrifying.
So the big crunch is terrifying. The big rip is also terrifying. The heat death is terrifying, but in a more existential way. In every case, one of the aspects of why it's terrifying is that we see it coming a little bit, right? Like we know that it's going to be predictable. So, but I can't, even though we're running a little bit over time, I can't let us go without saying that there's also ways that, we could just die tomorrow without any warning whatsoever.
Yeah. So my favorite scenario for the end of the universe, and people have very different opinions about this. Like a lot of people really don't like this idea, but my favorite is one called vacuum decay, and I like it partially because you wouldn't see it coming, because it would come totally by surprise, and in some sense you wouldn't even notice it. So the idea behind vacuum decay is, it's possible that there's a sort of instability built into our cosmos, and it has to do with the Higgs field, this energy field that's throughout all of space, that kind of is connected to how particles got mass in the early universe. The idea is that there's this big energy field that's throughout all of space, and what it's doing determines the laws of physics. And it was different in the very early universe. It had a different value, and that there was a shift. And when that shifted, it set the stage for physics as we know it. It allowed particles like electrons and protons and all these things to exist. It allowed electromagnetism to happen, and the things that make structure in the cosmos possible today. And it seems, as recent evidence has suggested, that it's possible that the Higgs field might shift again. And if that happened, that would be really bad, because we want physics to stay as it is. Well, I mean, it would, it would be completely disastrous for the universe, because how it would happen is that there would be some point in space, some random point in space, and at some random moment, the shift would occur. It's a quantum tunneling event. It's unpredictable. this shift would occur, and it would create.
Maybe it would happen in Harrisburg.
Yeah, maybe.
Possible.
I mean, it could. I mean, it could have happened at Saturn half an hour ago, and we just don't know it yet. But anyway, what happens is there's a little point in space where this shift occurs. It creates a bubble of a different kind of space, of where the Higgs field is different and the particle physics inside there is different. Electrons and protons and atoms can't exist in there, and that bubble expands out at about the speed of light and just envelops everything and destroys all structure in the cosmos. And the thing that makes people nervous about that is because it's a random quantum event, you can't predict when or where it would happen. When I try to reassure people, not that they shouldn't worry about vacuum decay, because I really believe you shouldn't worry about vacuum decay, there are a few things to say. One is that, obviously there's nothing you can do about it. Also, it's, you wouldn't notice it because it happens so fast. Like it's faster than your nerve impulses. You wouldn't even know it happened. So like, there's no tragic aftermath, it's just done. But also we can calculate based on our current understanding how long it's likely to take before that quantum tunneling event happens and anywhere in the observable universe. And we get a number like 10 to the power of 100 years. So we're pretty sure if it's going to happen, it's going to be a very long time from now, after essentially the universe is already dead. There's nothing really of interest left in it. But also we don't know for sure if it could happen, because the idea that vacuum decay is even possible is based on saying that, what we know about particle physics right now is all there is to know about particle physics, and nothing's going to come in and change that picture. And we're pretty sure that's not true. So we don't know for sure whether or not vacuum decay can happen, but I find it intriguing that something as small as a quantum tunneling event on a subatomic level could spontaneously destroy the universe at any moment.
Well, very good. Well, so at least this one, we are in agreement it's unlikely, right? Like the other ones, they're terrifying, but they're billions of years off. The one that it could be tomorrow is pretty unlikely, right?
Extraordinarily unlikely, based on our current understanding, more unlikely than, winning the lottery and getting struck by lightning at the same time while being hit by a meteor. I mean, it's you have to add a lot of very rare events to get to that point.
Well, good. So I think that's actually a wonderful segue from me asking you questions to asking the Q&A from the audience, because you mentioned that we're having this discussion on the basis of physics as we know it. So there's a question from an anonymous person who says, are your predictions of the end of the universe based on the current standard model? And I think it's lowercase standard model, so like of cosmology and relativity as well as particle physics. If there's a change in the standard model, would your predictions change?
Yeah. So, I mean, that's a great question. That's one of the really interesting, exciting things about this subject is that right now we have a standard model of particle physics, which is our current best understanding of how particle physics works. And we have what we call a concordance model of cosmology, which is our best understanding of how the universe works, the evolution of the cosmos. And both of those ideas, both those models, those sort of paradigms, have been borne out by the data. The data within some margin of error seems to agree very well with both of those models, where we have a universe that has dark energy, also dark matter, which I didn't talk about, but we can get into later if you want, invisible matter, and a history of the universe that goes the way I mentioned before. That's our concordance model. It has general relativity as the theory of gravity. All of that seems to fit the data very well. And then there's the standard model of particle physics, where we have a certain number of particles and forces of nature, and we know how things work on the quantum level. And that seems to fit the data very well. There are a couple of places where we might be starting to see cracks, but we're conservative about it. We're saying that we haven't fully discovered a break in the standard model of particle physics, but we're seeing hints, maybe, hopefully. And so, yeah, all these, these ideas about the end of the universe are dependent on these scenarios. So everything to do with dark energy is dependent on the concordance model of cosmology. vacuum decay is dependent on the standard model of particle physics. If either of those things change, we can have totally different scenarios for how the universe might end. And even, dark energy, along with dark matter, which is, as I mentioned, this invisible stuff that's most of the matter in the universe, neither of those fit into the standard model of particle physics, even though they're in the concordance model.
Right.
So they're indicating there's something new to be discovered, and they're most of the universe. So we're pretty sure we're going to find something to change this picture. We just don't know for the moment what we will replace these ideas with.
Okay, let me combine two questions because they're related. One is from Colleen, who says, is the universe expanding faster than the speed of light? And one is from Anne-Marie, who says, do we know what the universe is expanding into? These are some classic cosmology questions. I'm sure you've been asked them before.
Yes. So in terms of expanding faster than the speed of light, so the farther away something is, the more quickly it is receding from us. And that's just a consequence of the universe is getting bigger in the same way in every direction. So if you have something that's expanding uniformly, then the more distant things are moving away faster. It's like if you had a slinky and you were stretching the slinky between your hands, and you took a second to make it twice as big, then the two links sort of in the center of the slinky are only getting a centimeter apart over the course of that second. The ones on either end of the slinky are getting several feet apart over the course of that second. So they're moving way faster relative to each other, and that's the same, and all you've done is stretch the slinky in a very uniform way. So the more distant something is, the faster it appears to be moving away from us in a universe that's expanding the same way in every direction. And so, yeah, there are galaxies that appear to be moving away from us faster than the speed of light, but that's a distance-dependent statement. The galaxies that are only, maybe a few 100 million light years away from us are not moving away from us that quickly. So there's a region beyond which things appear to be moving at faster than the speed of light. But when we talk about the expansion rate of the universe, the way we express it is in terms of a speed per distance rather than just a speed, right, because it is dependent on distance. The other question about what the universe is expanding into, so we don't have any evidence that there's an edge to the cosmos, that there's a boundary of any kind in space. And so, part of it depends on how you define universe. So if universe is everything, then there's nothing outside the universe. So there's no expanding into because there's no external space. But we can also conceive of a cosmos that is expanding but doesn't have any boundaries, doesn't have any edges. We can conceive of a universe that's infinite and just getting sort of infinite-er over time, and those are consistent with the mathematics. Those are consistent with the observations. So we don't have any evidence that there is something outside the universe is expanding into. What we do observe is that things within the universe are getting farther apart, and that's really all we can say about the expansion, that things within the universe are getting farther apart.
Okay, let me do again the combining two questions idea. There's one from Tom that says, roughly speaking, he says, are we going to figure this out soon? What is the rate of progress that we're making on understanding these questions? And then an anonymous person says, what are the discoveries you think we'll make in the next 50 years that bear on these ideas?
Yeah. So, I mean, those are tough questions because it's very hard to predict what we will discover in the future. Because a lot of this depends on what dark energy is, and because if it's a cosmological constant, we can't ever say for certain 100% that it is that because of the limitations to our measurements. We can't really say for certain that a certain observation that we're going to do is going to clinch this, absolutely settle the question. I think that we are making a lot of progress in understanding the expansion history of the cosmos. We have new telescopes that are coming out soon that are going to show us the history of the cosmos to more and more detail, that are going to observe more and more galaxies and supernovae and really map out cosmic history to extraordinary detail. And those should give us some hints about dark energy, some insights into how dark energy works, and also how dark matter works. And that might tell us something about how we should understand particle physics and matter in the universe. And so I think that there's a lot we're going to learn. And we're also learning more about gravity by detecting gravitational waves, where we can detect the ripples in space itself as black holes are colliding in other galaxies, which is amazing. So we're learning a lot about all these topics, and we're going to learn a lot on the experimental side with new accelerators and colliders and new detectors for various things. But whether or not we're going to clinch this question, whether or not we're going to say for sure, like, we know how the universe works, we know the total, overall structure of the cosmos and how it's going to end. I think that's something that we really can't make any solid predictions about when that insight will come, or if we'll ever know with any kind of degree of certainty exactly what's going to happen, because it's the future, and there's always going to be uncertainty about the future. But I do think it's an extremely exciting time. I do think we are making progress very rapidly in our understanding of a lot of things, and in our sort of observations of the cosmos. And I'm very excited to see what we find out. And maybe it'll be something totally new. Maybe we'll find some new exciting way for the universe and that we haven't talked about before.
Maybe this is related to a question that came up from Sid Verma, which is, how do you measure dark energy? I mean, I guess you didn't give us the exact story, like, for example, of the supernovae that were used to originally give us the hint the universe is accelerating.
Yeah. So what we do is we try to figure out how quickly the universe is expanding now and how quickly it was expanding in the past. And the way we do that is we look for sort of distant objects, and we try and determine how quickly distant objects are moving away from us, and we can see more and more we see more and more distant objects. We measure how quickly those are moving away from us, and we extrapolate from that how quickly they were moving in the past, because we're looking at the past. When we look at the distance, we do a little bit of complicated mathematics with that, and it gives us an expansion history. The reason supernovae are involved is because one of the things that's really difficult about measuring the expansion history of the universe is that you have to know two things. You have to know how far away something is and how quickly it's moving away from you. And weirdly, it's a lot easier to measure the second thing. It's a lot easier to measure how quickly something's moving away from you, because there's this property of light that when something's moving away from you very quickly, the light stretches out to a longer wavelength, a lower frequency. And so it's called redshift. So we can measure the shift of the light to see that something is moving away from us more or less quickly. But actually knowing exactly how far away that thing is quite hard in the cosmos, because we don't have mile markers. We can't lay out a ruler. And so we have to build up a picture of, a sort of set of measuring methods to see how far away something is. And supernovae, a certain kind of supernova, type 1A supernova, which is a supernova where a white dwarf star, a remnant of a sun-like star, explodes. Undergoes a thermonuclear explosion when it is hit with another star, basically, or material from another star. When that explosion occurs, it occurs in a way that is fairly regular. So the ones that explode nearby and the ones that explode far away seem to be going through a very similar process. And so if we know how far away the nearby ones are, and we see how bright they are, and we know how bright the distant ones are, then that can tell us something about how far away they are. Because all you measure is a brightness of something. If you also know the distance, then you have those two pieces of information. If you have the brightness of the brightness of something, and you know that it's the same brightness as something nearby, then you can calibrate the distance, because you know how dim it should be, how dim it should appear by being farther away. So there's this sort of complicated process of setting various kinds of measuring methods, but supernovae are useful because we think we know how bright they really are. So by knowing how bright they look, we can tell how distant they are.
Okay, I'm going to try to squeeze in 2 more questions in the remaining 30 seconds.
Okay.
The first one is, well, we can go over a little bit. No one's going to care. The first one is from Cheryl, who wants to know about your background. How did you gravitate to this subject area? What was it that made you interested in astrophysics?
Okay. I've always been fascinated by the cosmos. So I got into astrophysics really through the physics side. I know a lot of people get into astrophysics through the astro side. A lot of my colleagues, grew up looking at the stars and being fascinated by constellations and planets and things like that. I grew up in Los Angeles. The sky is pink. You see 10 or 20 stars every night, maybe a planet if you're lucky. You don't grow up with a fascination with the night sky when you grow up in LA, because you just don't see it. So what I got into was I just wanted to know how everything worked. And I was the kind of kid who was a tinkerer. I was taking things apart, putting them back together, trying to understand the workings of everything. And that just kind of extended into physics, into trying to understand the workings of the universe. Why do stars shine? Why do planets orbit? What is time? What is space time? What are black holes? These increasingly grand questions all sort of came from this idea that I just wanted to understand how things work and what's at the bottom of everything.
And the last question, which I think is a great question to end on, if I can find it, from Betsy. I love the quote you chose from Carl Sagan. "We are a way for the cosmos to know itself." What does that quote mean to you?
So to me, I don't know if we are the only intelligent things in the universe. Earthlings, there are other intelligent species, I think, on Earth. There are different kinds of intelligences, parrots and dolphins and octopus and all of those kinds of things. But we were built by the cosmos. We were built by the processes of physics and chemistry and biology. Things came together through gravity. Chemistry occurred. Life appeared, and now we are able to contemplate back all of those events. We are able to look out into the cosmos and understand it. And I think to me, that's incredibly inspiring, because when you learn more about the cosmos, you learn that we are really insignificant on the grand scale. Not only are we just one species on one planet orbiting one star in one galaxy out of trillions of galaxies, or hundreds of billions or trillions of galaxies in the observable universe. The kind of stuff we're made of, regular matter, is insignificant in the cosmos. It's 5% of what the universe is made of. The rest is dark matter and dark energy, which we don't really understand and can't really interact with, except through gravity in case of dark energy or dark matter. And so we are deeply insignificant on every level, and yet we are able to understand the history of the cosmos down to fractions of a second. We are able to see the Big Bang. We are able to observe the expansion of the universe. We are able to know so much about the universe that created us through these amazing physical processes. And so I find that's what I find really inspiring about that, is that we are creatures of the cosmos, built by the cosmos, and now we are able to understand the cosmos despite being deeply unimportant in every way.
I think it's actually, in a perverse way, an uplifting message, how insignificant we are, because the whole universe is going to end. We're not going to build a structure. Ozymandias, wasn't right. You can't build something that people will look at and despair forever and ever. But like you say, we can understand the universe. We can write books about it. We can buy books that other people have written. So
Yes, you can.
Thanks very much, Katie Mack. Thanks, Alex, for hosting this, and thanks everyone for being in the audience. It's a great time.
And thanks so much, Sean. This was really great.
My pleasure.
Thanks, Sean. Thanks, Katie. Just want to say a quick reminder to our audience: if you'd like to purchase The End of Everything, you can purchase it itself, or you can purchase a book bundle. Look in the chat room, or simply go to midtownscholar.com. Thank you again to Sean and Katie. Katie, congratulations! Paperback now out in the world for the first time, and thank you to our audience again for tuning in. So many good questions. Sorry we didn't get to everything, but thanks again, and everyone have a good night.
Thanks, everyone.